Welcome students. Welcome to the course of Mechanics of Fluid. Myself Sanjay Manuel, Assistant Professor, Rajagiri School of Engineering and Technology. So in this class we will understand some important concepts like continuum concept. We will understand what are the different fluid properties, especially viscosity, how it is important, how it has been influencing the fluid motion, and different types of fluids based on viscosity. We'll learn this one in detail. Okay, first we will start from continuum concept. We know that matter consists of number of atoms, and the property of a system will be defined, or the matter will be, or the behavior of a matter will be defined based on the activities happening at the atomic level. So the atomic level activities for a bulk substance, if you take a small region, there the action will be different from that of if you take another region, because there exists discontinuity and the activities happening at atomic level is entirely different. But if you are taking the system which we take into consideration, if the length scale of that system is very much higher than that of mean free path, then the atomic level induction, or in other words micro scale activities, can be neglected, and we can assume the substance is continuous in nature and the property remains the same throughout. Okay, which we will define with the help of a number called as Knudsen number. It's a ratio between mean free path and the dimension of the system. So if the value of mean free path is very much less compared to the actual length scale, we can assume the system to be in continuum. Most of the practical applications are coming under continuum concept. So we'll take this continuum concept throughout our course, because we are taking systems with length scale very high. We are not taking any system with smaller length scale and evaluating it. We are studying all the practical applications where the system is very much higher than that of the length scale of the system is very much higher than that of the mean free path.
Exemptions to continuum concepts comes when the length scale that you take into consideration is very small, that is, it is in the microscopic range. Then the individual atomic activities has to be taken into consideration. Some of the example or the some of the theories that is been used is rarefied gas theory are some of the examples. Now this happens, we will accept continuum assumption when pressure tends to zero for a small volume, or just the reverse. If volume tends to zero for at a particular pressure, then we cannot take continuum concept. There the properties will be depending upon how individual molecules behave, so there discontinuity exists. So in order to define that, if we plot the density with respect to the size of control volume, we can see in which case we can take continuum assumption and which case continuum assumption is neglected, or we have to consider the discontinuity of the system. So in order to define that, we are using a number called as Knudsen number, which is ratio between the mean free path lambda of the molecule and L, which is the characteristic length dimension of the system. If characteristic length dimension is very high compared to mean free path, which we have taken previously, we will be taking into consideration the continuum assumption. But if it is comparable with characteristic dimension, then we have to take the discontinuity into consideration. So here, if lambda by L, that is, if the Knudsen number is lesser than that of 0.01, then we can take continuum assumption. But if the value is between 0.01 to 0.1, then we will be assuming that one has slipped flow, and the next one 0.1 to 0.01. If I am taking the Knudsen number between that, then we have to take transition flow, and if it is greater than 10, we have to take free molecular flow. There the molecular properties to be taken in greater extent. So for our condition we are taking continuum assumption. For our course we are taking continuum assumption. Okay, now next we will just refresh what we have learned in the junior classes. What is a system? What is a surrounding? System is a region where we are doing our observation, and anything other than system is called as surroundings. Between system and surrounding there can both exist matter exchange as well as energy exchange. Depending upon the way in which exchange happens, we can define that one as open system, closed system, and isolated system. Then the system itself can be taken into two different cases. It can be control volume system, which has been shown at the bottom part. A control volume with, it can be of real boundary, or it can be of imaginary boundary, or we can take control mass system, where the mass of the system remain the same even if the volume varies, which is be shown at the top. Okay, now based on this we will be defining different properties of a system, and for fluid system also we will do the same. We can assume in fluid systems usually we will be taking control volume system. We will take control volume approach, where the volume is assumed to be fixed. There can be a mass flow coming in and going out. For our reasons, a control volume system approach is being taken for fluid mechanics. Okay, now any characteristic which is used to describe a system is called as properties, and these properties can be of two different types, intensive and extensive in nature. If you are taking intensive property, it is independent of the mass, and if you are taking extensive property, it is dependent on mass. If you take a system whose values of mass, volume, temperature, pressure and density Bm, Vt, P and rho, and if you take the same system and divide into half, you can see the mass will become 0.5 times m, volume will become 0.5 times v, but temperature remains the same for individual systems, pressure remains the same for individual system, and density remains the same for individual systems. From here you can understand m and v, the mass and volume, are examples of extensive property, whereas temperature, pressure and density are extensive property, because it doesn't vary. The intensive property doesn't vary with respect to how much time you slice the system, still the intensive property value remains the same, but extensive property depends upon the mass of the system.
Next we will be learning different fluid properties. First we will be taking into consideration basic properties of fluid, which can be defined as characteristics of a continuous fluid which are independent on fluid motion. Okay, so first basic property of a fluid comes is density. As you already know, density is the ratio between mass and volume. So the SI unit of density is kilogram per meter cube. The density of water is 100 kilogram per meter cube, and density of air is 1.24 kilogram per meter cube. Density of mercury is more than that of water, which is 13,600 kilogram per meter cube. Now once we know density, just reverse of that one is the next important property called as specific volume. Specific volume is the ratio between volume per unit mass. Volume per unit mass is defined as specific volume, which is actually the inverse of the density. So here we will be defining the unit of specific volume is meter cube per kilogram. Next, when you take into consideration fluids, okay, we will be having another terminology called as specific weight. The specific weight is the ratio between weight to volume. Weight to volume ratio is specific weight. So the unit, the SI unit of specific weight is Newton per meter cube. Now here, if you take density, and specific weight, what would be the difference? What would be the difference between specific weight and density? In the case of specific weight, it is ratio between weight and volume. In the case of density, is the ratio between mass and volume. So if you relate between density and specific weight, its specific weight will be equal to density into 9.81 meter per second square, that is the acceleration due to gravity. So that's why the specific weight of water, since the density of water is 1000 Newton per meter cube, the specific weight of water will be 9810 Newton per meter cube, and for air it will be 12.07 Newton per meter cube. Now when you relate when you compare two different liquids or fluids, we usually define it based on another terminology which is called as specific gravity. This is actually the ratio between density of a substance to the density of a standard fluid. Okay, so it will be this the standard fluid will be at a particular temperature. In the case of liquids, it is taken as water at 20 degrees Celsius, and the density of water at 20 degrees Celsius, and similarly for gaseous form, it is the specific density of air is being taken as the standard substance. So the specific gravity is the ratio between specific, if you take the case of liquids, it is the ratio between specific weight of liquid divided by specific weight of water. But if you take the gaseous form, it will be the ratio between specific weight of gas divided by specific weight of air. So previously we have learned what is the value of gravity density for water as well as for mercury. So from there we can get the specific weight, so specific gravity of water will be equal to 1, and specific gravity of mercury it will be 13.6. This specific gravity is useful when you go for analysis of different fluid properties. When you come to the next phase, when we study how to measure the pressure at different point with the help of manometer, we will be utilizing this terminology called as specific gravity. So right now we have studied some terminology. Some of them are gravity, density, specific volume, then specific weight, and then we have studied specific gravity. Say I am asking you, say I assume that I am taking two different fluids or two different densities which are immiscible. Then if I am taking the case of oil and water, if I am pouring oil and if I am taking water, say assume that the density of oil is much more higher than that of water. In such case, what would happen? The liquid which is having more density will be going down, and one which is having lesser density will be moving up. Okay, that's what happens. So from there, okay, if I am taking two different liquids, water and silicone oil, two different liquids which is of almost the same density, 1000 kilogram per meter cube for water, and for oil it is 970, the silicone oil it is 970 kilogram per meter cube. The density is almost the same, but here you can see the way in which water flows and silicone oil flows is entirely different. Can you tell me what may be the reason behind it? You can see the silicone oil is being poured into a beaker. It's much more slower. In the previous phase, I have shown you the water is being poured into the same beaker, but the flow rate obtained for water was much more higher compared to silicone oil. Can you tell me what would be the reason? Here you can see the densities are almost the same. It's not due to the density difference. Can you tell me what would be the reasons behind it? Yes, we'll explain it based on a new phenomena. Okay, so for that, first of all, I am taking, instead of fluid, I am taking the case of two solids. I am taking two solids A and B, assuming two solids A and B, on let A be at stationary condition and B be moving with the help of under the application of a force F, let B will be moving forward. Okay, when it is moving forward, what happens? When two solid bodies come in contact, there will be always friction between the at the contact surface. Similarly, for fluid also it happens. It may be when you compare with solid and fluid, or there also the resistance of flow occurs. There will be a resistant force existing. Similarly, if you take two different fluid layers, okay, there also you will be having this restricting force, this resistance for, if you take the case of water and silicone, in the first case, in which case you can say in which case you will be having more resistance? Is it in the case of water or is it in the case of silicone oil? Yes, it's in the case of silicone oil. The resistance, if you move hand through water and if you move hand through oil, at which condition you will be having more resistance? You can see that the more resistance will be available in the case of oil. When you move your hands through the oil, you will be feeling more resistance. So this will be actually acting as a property. This property that represents the internal resistance of this fluid is called as viscosity. We'll go in detail what is viscosity and how we'll be defining. Now the viscosity, the way in which viscosity is being explained is based on Newton's law of viscosity, which is obtained by an experimental study by Sir Isaac Newton. So in his experiment study, what he done is he taken a stationary plate, and above that he have taken two different plates. In between that you will be having fluid layers which moves now, which is free to move. Now he kept one of the plate to be stationary in nature, and the second one he gave a force F on that one. So due to that, the plate moves with a velocity u max. Okay, and here the velocity of the plate will be 0. So that's why the fluid layer adjacent to this one is having a velocity equal to 0, which is called as no slip condition. Okay, that is the velocity of the stationary plate, and the layer adjacent to the fluid layer adjacent to the plate will be having the same speed. So that is called as no slip condition. Similar to that, the speed of this corresponding upper plate, the upper moving plate, and the layer of fluid just adjacent to this one will be having the same speed, since it is assumed to be no slip condition. So in such condition, you can see the speed varies as you move up from the stationary plate to the moving plate. So when that happens, in that condition, he observed that the force F is directly proportional to the area. The area he chose, if it is more, then the force required will be more. As you already know, as the area increases, the resistance that will taking up will be also higher. Now the velocity v, it will be directly proportional to velocity v, that is the speed at which it is moving. Okay, then it is inversely proportional to the length. The resistance is inversely proportional to the length, that is the distance between the two plates. If the distance between the two plates is less, then you will be having more resistance. If the distance between the plates is less, so higher, you will be having less resistance. So from there he found out that the force is directly proportional to area of the plate, velocity of the fluid, and L will be the distance between the plates. Now as you already know, here the force is acting tangential to the surface A. The force is acting tangential to the surface A. So that's why here we can assume this one as a tangential force. The ratio of tangential force to area, or the force divided by the area, is defined as the shear stress. So you can define F by A. That is, if I am taking this one, if I am equating this, if I am taking A to this side, F by A you can define as tau, and this V by L. V is the velocity and L will be the distance between them. So here you can see the variation of the velocity with respect to the distance. Here you can see, here it is increasing in a linear manner. The increase of the velocity will be in linear manner. So that's why you can define V by L, that is the velocity at extreme divided by the distance between the plates, is directly will be equal to the slope of this graph between the distance x along x direction and the velocity distance along the y direction and the velocity. It will be the ratio between, it will be the slope, it will be acting as the slope of this corresponding plot between the velocity and y. So from there we can define V by L, we can define it as du by dy, where u defines the velocity and y defines the distance between the plates. So if you are taking that, you will get tau will be directly proportional to dou u by dou y. Now in order to avoid this proportionality, we will be introducing a constant called as mu, which is called as coefficient of viscosity, which acts as a property of the fluid. Now here you can see the shear stress will be more at which condition, when if I am taking the two different fluids which is under the same condition. Here mu will be equal to mu into dou u by dou y. So if you take dou u by dou y, let it be the same. In which condition you will be having more shear stress acting? In the case where you will be having more mu value, so more resistance will be obtained for that condition. So more resistance means the value of mu will be also higher. So this mu value is called as coefficient of viscosity, or it is also named as dynamic viscosity or absolute viscosity, which acts as a property of a fluid. Okay, now the unit, the SI unit of dynamic viscosity is Newton second per meter square or Pascal second. In CGS system it is called as Poise. Now the Poise and Pascal second is been coming in ratio as 1 Poise will be equal to 0.1 Pascal second, and the viscosity of water at 20 degree will be 1 centipoise. Okay, so as I already explained, viscosity can be defined from Newton's law of viscosity, which is mu will be, the shear stress will be equal to mu into dou u by dou y, where mu is the coefficient of viscosity or dynamic viscosity. So we will be explaining it in detail the same. We will just explain it once again. If in the Newton's experiment, he had taken a lower plate which is stationary, and he had taken an upper plate which is moving with a velocity v, and when it moves, the velocity of fluid adjacent to the lower plate will be having 0, and the velocity of fluid adjacent to the top plate will be having velocity v, and the distance between, if I am assuming the distance between the plates, let it be L, and if I am taking the condition which I already explained, that is a fluid particle which is adjacent to the lower plate will be having the same velocity as that of the plate. So that condition is called as no slip condition. So since the velocity of bottom plate is 0, the velocity of fluid particle adjacent to that will be having the velocity 0. Similarly, the velocity of fluid particle adjacent to the top plate will be having velocity v. Okay. Now the variation of velocity is being shown in this diagram. Along the y direction, the velocity variation is being shown, so which is linear in nature. So the slope of this one you can find it like this. Okay, the inverse of the slope will be coming like this, du by dy, which is equal to v by L. Since the profile is linear in nature, you can define du by dy will be equal to v. Okay, here we will be taking two different plates, bottom plate and top plate, which is kept at a distance L, and we have taken a fluid film LMNO. When the upper plate is given a force F, it will be deformed to form LMN-O dash. So the position of N and O will be changing to a new location. If I am taking just the location, a new location of N, let this be the initial condition, and after a time t, after the deformation, the location of N, let it be here named as N dash. So the distance traveled by the fluid particle at point N is taken as dA, then it will be equal to velocity into the time taken. So that is dA will be equal to V into dt if I am taking it like this, and the angle subtended by N and N dash with respect to M is taken as d beta. This d beta will be your shear strain. This will be your shear strain. In the case of solid mechanics, we have learned how we will be defining shear strain when it is been applied by a shear force. Okay, similar to that, the angle subtended by the initial location and the final location after deformation, the angle subtended between them is taken as the shear strain. So here also d beta will be acting as the shear strain. Now what is tan beta here? Tan beta will be equal to V into dt or dA divided by L. So that's why we can define that one as tan d beta. If the d beta is very small, we can define tan d beta will be is approximately equal to d beta, which is equal to dA divided by dL, which is equal to V into dt divided by L. Or we can write d beta divided by dt will be equal to V by L. We have already defined V by L is equal to du by dy by defining the velocity profile. We have defined d beta V by L will be equal to du by dy, or in other words we can say d beta by dt will be equal to du by dy. Now in the previous case, in the case of Newton's experiment, we defined shear stress will be equal to mu into du by dy. So from the new relation we can define that one is equal to mu into d beta divided by dt. What is d beta divided by dt? D beta is what? Shear strain. So d beta divided by dt will be equal to rate of shear strain. So from here, Newton's law of viscosity defines the shear stress is proportional to rate of shear strain in the fluid. It's entirely different from that of solids. In the case of solids, according to Hooke's law, shear stress is directly proportional to shear strain. But here, for fluids, according to Newton's law of viscosity, shear stress is proportional to rate of shear strain. So from here you can understand the difference between both in the previous example. First case, water was free to flow. In the second case, the silicone oil was not that much free to flow. The reason behind that one is the density of water is 100 kg per meter cube. The flow, we can see the flow, and the density of that one is silicone oil is 9700 kg per meter cube, but the flow is different from the previous one. The reason behind that one is the viscosity mu value. The dynamic viscosity value is 8.90 into 10 raised to minus 4 Pascal second for water, but whereas for oil it is 9 Pascal second, which is very much higher than that of water. So that's the main reason behind the difficulty in flow for silicone oil compared to water. So this is another reason. The object moving through, if you take an object moving through honey and an object moving through water, it is entirely different. It is due to the higher viscosity of honey. Okay, now next we will be understanding the variation of viscosity as temperature increases. For fluids, the variation of temperature with respect to viscosity with respect to temperature will be different for liquid as well as gas. The reason behind that one is, from the diagram you can see the variation of viscosity for liquid, it is as temperature increases the viscosity also decreases, that is why resistance also decreases. But for gas it's not the same. Here as temperature increases, the viscosity also increases. So that's why the main reason behind both the case. In the first case, the influencing parameter for viscosity is the cohesive force. Cohesive force means the attractive force between adjacent molecule of the same type. Okay, so in the first case, the way viscosity in liquid is due to the cohesive force, and that varies as temperature decreases. Now next, viscosity variation in gases. The variation in liquids, which is mu, will be equal to A into 10 raised to B divided by T minus C, where A, B, C are constants and T is the temperature. So this is a variation of dynamic viscosity with respect to temperature. But for gases, it is due to the intermolecular collision. The collision of molecules increases as temperature increases, which leads to increase in viscosity. It is defined based on the correlation mu will be equal to A into T raised to half divided by 1 plus B divided by T, where A and B are constants and T is the temperature. Okay, next we will be understanding an important constant called as kinematic viscosity, which is the ratio between dynamic viscosity and density of the fluid. Now the SI unit of this one is meter square per second, and the CGS unit of this one is centimeter per second. Another name for that one is strokes. Now the variation of mu is not that much stronger as there occurs a change in pressure. But when you take the case of the kinematic viscosity, the gas varies, the value of kinematic viscosity varies with pressure, since it is depending on density. So next we will be going through some of the problems from the property dynamic viscosity and kinematic viscosity. First question: a plate weighing 150 Newton and measuring 0.8 meter into 0.8 meter slides down an inclined plane over an oil film of 1.2 mm thickness for a inclination of 30 degree and a velocity of 0.2 meter per second. Compute the dynamic viscosity of the fluid. Second question: in a stream of glycerin in motion, at a certain point the velocity gradient is 0.25 second raised to minus 1. If for the fluid the density is 1268 kg per meter cube and kinematic viscosity is 6.3 into 10 raised to minus 4 meter square per second, calculate the shear stress at the point. Okay, next we will be understanding different types of fluids that is been available. Now the first type is Newtonian fluid. The Newtonian fluid are fluids which obeys the Newton's law of viscosity. All the type of fluids which obeys Newton's law of viscosity, which I learned in the previous phase, that is shear stress is equal to mu into du by dy, or in other words we can say the shear stress is directly proportional to rate of shear strain is Newton's law of viscosity. The fluids which obeys this one is called as Newtonian fluids. So if I am taking a plot between the rate of shear strain and shear stress, you will get a plot which is a straight line, that is it will be linear in nature, and the slope of this one will be the dynamic viscosity. So if I am taking the dynamic viscosity, let this plot be for water. If I am taking another fluid, and so it obeys so the water obeys Newton's law of viscosity, which is mu is equal to mu divided du by dy. The shear stress is equal to mu into du by dy. So if I am taking another fluid which also obeys Newton's law of viscosity. Now in this plot, let this be oil. So can you just compare between oil and water? Here you can see in the first case, in the case of water you will be having a smaller slope, but in the case of oil you are having a bigger slope. That means the dynamic viscosity is higher for oil. Now the fluid which obeys Newton's law of viscosity is called as Newtonian fluid. The most common fluids are water, air, gasoline, oils, etc. are some of the examples of Newtonian fluid. Now here the viscosity is independent of rate of shear strain for Newtonian fluid, but all fluids are not Newtonian in nature. All fluids may not be obeying Newton's law of viscosity. There are some exceptions, but in this course we are studying in detail only the Newtonian fluids. But we will just go through what are the different options other than Newtonian fluid. What are the other classification of fluid that is been available to you? Okay. Such fluids which does not obey Newton's law of viscosity is called as non-Newtonian fluid. That means if you are taking a shear stress to rate of shear strain graph, for Newtonian fluid it will be linear in nature, which we have learned in the previous phase. Now we will go through different cases of a non-Newtonian fluid. If it is first case, if it is an ideal fluid, then the viscosity will be equal to 0. Okay, that means with small shear stress the deformation rate will be infinity. Okay, now we will take another option. If you take a plot like this, the shear stress to rate of shear strain plot, if it is like this, from here you can see if at the bottom part the slope is higher. As it moves, as the rate of deformation varies, the slope will be smaller in nature. That is, the viscosity will be, initial phase viscosity will be higher. As the rate of deformation increases, the rate of shear strain increases, the viscosity decreases. So arbitrarily, if I am taking a location and finding the slope, it can be defined as the apparent viscosity. Such fluids are called as shear thinning fluids or pseudoplastic. Some of the example, if I am taking pseudoplastic, when you give large shear stress on the corresponding body, it will be comparing if the shear rate is high, then viscosity becomes smaller. Some of the examples are paint, polymer, etc. Paint, if you see one of the example, those who have seen paint, after a long period of time it will be hardened much more. The viscosity, the flow ability of that one will be, the resistance to flow will be much more higher as we go. So before painting, people will be just shaking it at a higher shear rate so that the viscosity gets reduced. When he increases the shear rate, the viscosity also decreases, so it will be easy to flow. Another option is the case where in the first case, in the initial phase, you can see the viscosity was higher, viscosity was lower. As the shear rate increases, it will be increasing the viscosity, the slope will be increased. So such fluids are called as shear thickening fluids or dilatant fluids. As shear stress, larger apparent viscosity will be obtained. That means it becomes much more viscous as the shearing rate increases. It becomes harder and harder. The example is suspended starch, sand, etc. Some of the examples. Okay, the application of this one is being utilized in many. Another case of non-Newtonian fluid is the viscosity variation. There will not be any deformation until or unless the shear stress is reached to a permissible limit. After that, it will be acting similar to Newtonian fluid. Such fluids are called as Bingham plastics. So this type of Bingham plastics actually resists the shear stress up to a finite value, then deforms continuously. So just go through this. This is very important for your university exam as well as those who are applying for GATE, this topic is very important. Examples of Bingham plastic is toothpaste. Now the variation, if I am taking instead of Newton's law of viscosity, if I am modifying the Newton's law of viscosity, if I am taking the equation, it will be equal to shear stress will be equal to A plus B into du by dy raised to n, where A and B are constants and n is an exponential constant which has been used to define whether it is shear thickening or shear thinning fluid. So it is general equation used for non-Newtonian fluids. So if I am taking Bingham plastic, the value of A will be equal to the finite value beyond which it has to be applied for the deformation of the fluid, and mu will be acting as the B. In all the case, mu will be acting as B, and here the value of n will be equal to 1. And the second case, the value of A will be equal to 0. That is, for shear thickening fluid, the value of A will be equal to 0 and value of B will be equal to mu. B will be equal to mu, and value of n will be always greater than 1. The value of n will be always greater than 1. And in the second case, mu will be equal to B into du by dy raised to n, where the value of n will be always less than 1 and value of A, according to the general equation, the value of A will be equal to 0 in this case also.